Imagine plugging in one extra cable and watching an entire network melt down in seconds. That's the world without spanning tree protocol. Welcome to Stage 2, Lesson 12 of our IT Networking Mastery curriculum. Over the next few minutes, we're going to unpack how switches quietly cooperate behind the scenes to keep your network loop-free, stable, and fast. Here's the roadmap for the next few minutes. First, we'll look at why Layer 2 loops aren't just an inconvenience. They're genuinely catastrophic, capable of taking down a network in seconds. Then we'll see how switches elect a root bridge entirely on their own, with no manual intervention. From there, we'll break down the 3 port roles: root, designated, and blocked, and finished by walking through the port states and how long convergence actually takes. So let's start with the problem itself. Picture 3 switches wired in a triangle, A, B, and C, and a single broadcast frame enters the network. Switch A floods it to B and C, B floods it back to C and A, C floods it back to A and B, and because Ethernet has no TTL field, that frame never dies. Within seconds, broadcasts replicate endlessly, CPUs hit 100%, MAC tables flap as the same addresses appear on different ports, and the network is effectively gone. The fix arrived in 1985, courtesy of Radia Perlman, and it's genuinely elegant. Spanning tree protocol lets switches discover each other, agree on a single root switch at the top, and then logically shut down the redundant links. So between any 2 switches, exactly one path exists. The physical mesh stays intact, but logically it becomes a tree. And it happens in 3 steps. First, elect a root by voting. Lowest is a bridge ID wins. Second, every other switch picks its one best port toward that route based on link speed. Third, on any segment where loops could still form, all but one port get blocked. No loops possible, but the backup links are still sitting there, ready to wake up the moment something fails. So let's zoom in on step 1. That root election. Every switch builds a bridge ID by combining a 16-bit priority value with its 48-bit MAC address, and the switch with the numerically lowest bridge ID wins. In this example, 3 switches are sitting at the default priority of 32,768, but switch C has been configured down to 4,096, so it wins instantly, no MAC tiebreaker needed. And that's the real lesson here. Don't leave root selection to chance. Set the priority on the switches you actually want as root. So the election is deterministic instead of decided by whichever box happened to have the lowest MAC address from the factory. Once that root is chosen, every other port in the topology settles into one of 3 roles. On each non-root switch, the single best path back to the root becomes the root port. That's the RP you see on switch A and switch B pointing up at switch C. On every active segment, one side is elected the designated port, the DP responsible for forwarding frames onto that link, and anything left over, the redundant path that would otherwise form a loop, gets put into the blocked state, like the link between A and B here. 1 role per port, and the loop is mathematically broken. But assigning those roles doesn't happen instantly. In classic 802.1d, a port crawls through a fixed sequence before it can actually pass traffic, from blocking, where it only listens for BPDUs, into listening as the topology is built, then learning where it starts populating the MAC table, and finally forwarding. Each transition burns 15 seconds or more, so from the moment you plug in a cable to the moment data flows, you're waiting 30 to 50 seconds. For a desktop, annoying. For VoIP or a server failover, that's an eternity, and it's exactly the pain point that RSTP, coming up in Lesson 13, was built to fix. Now, all of this election and role assignment depends on switches actually talking to each other, and the language they speak is the BPDU, the Bridge Protocol Data Unit. Every 2 seconds, the root bridge emits a configuration BPDU carrying its bridge ID, the path cost, sender info, and timers, and every other switch relays it downstream so the whole topology stays in sync. If 20 seconds pass without hearing one, switches assume the root is gone and start a new election. There's also a second flavor, the topology change notification, or TCN, which fires upstream the moment a link changes, telling everyone to flush their Mac tables and drop the aging timer to 15 seconds so the network can relearn quickly. Think of it as STP's pulse, steady heartbeat in normal times, urgent alarm when something breaks. So, how does a switch actually decide which path to route is best? It uses cost, and cost is tied to link speed, where faster links carry lower numbers. Under the original 802.1d scale, a gig link is 4, 10 gig is 2, and old 100 meg is 19. The newer long scale just gives more room to differentiate modern speeds. The key idea is that cost is cumulative. A switch adds up every hop between itself and the route, and whichever port gives the smallest total wins route port. So 2 gigabit hops at cost 8 beats a 1 gig plus 100 meg path at cost 23 every time. Now on a Cisco switch, STP is already running the moment you plug things in. But leaving the route election to chance is a rookie mistake. You want to deliberately pick your route, usually your strongest core switch, by lowering its priority to 4096, or by using the friendlier route primary macro that figures out the right value for you. Then, show spanning tree VLAN 1 confirms who actually won, what the cost looks like, and which port is your route port. And one more habit worth building early. Enable BPDU guard on access ports. So the second some rogue switch shows up where an end device should be, the port shuts down before a loop can ever form. Now, BPDU guard is just one piece of a bigger picture because classic 802.1d has several weak spots worth knowing. It's slow, 30 to 50 seconds to converge, which RSTP fixes in the next lesson. Access ports sit through that whole delay unless you enable port fast, but port fast alone is dangerous. If someone plugs a rogue switch in, you get an instant loop, which is exactly why BPDU guard exists. And if that rogue switch has a lower bridge ID, it could even hijack the route role. Route guard prevents that. Finally, the original spec ran one single tree for every VLAN, wasting half your links. PVST Plus and MSTP solve that by giving each VLAN or group of VLANs its own tree. So let's lock in what matters from this lesson. Layer 2 has no TTL, which means a single loop can melt your network. That's the whole reason STP exists. The route bridge is whichever switch has the lowest bridge ID, and you should always set that priority manually on your core, so the topology isn't decided by accident. Remember the 3 port roles: route, designated, and blocked. Know that classic STP is painfully slow at 30 to 50 seconds, and never, ever leave an access port without port fast and BPDU guard. Keep this cheat sheet close. It's everything you need at a glance. Bridge priority lives between 0 and 65,000, defaulting to 3D2SF68 in jumps of 4096. Ports walk through disabled, blocking, listening, learning, and finally forwarding. BPDUs go out every 2 seconds, but a TCN BPDU is the special one. It signals a topology change and flushes the MAC tables. And for path cost under 802.1d, remember 1 gig costs 4, 10 gig costs 2. And that wraps up our deep dive into classic STP. Next up in lesson 13, we're stepping into the modern era, RSTP and MSTP, where convergence drops from nearly a minute down to under a second, and you get separate spanning trees per VLAN group for smarter load balancing. If this lesson clicked for you, head over to dargslan.com or subscribe on YouTube, and I'll see you in the next one.